Please remember to turn your cell phones down. That'd be appreciated. If you didn't download and print the copy of the slides for this session before your arrival, you can still download the PDF by using your phone or tablet to scan the QR code on the title screen or the final slide of today's presentation. Our speaker today needs no introduction, but is a member of ESA's technical support staff. You can read his complete bio on ESA's convention mobile app. I will use this microphone. If you have a question, raise your hand. I'll get to you as soon as possible so we can all hear the question. Please join me in welcoming Chuck Young.
Thanks, Mike. Welcome, everybody. I see quite a few younger faces here, so just as a real quick, how many of you have been in the industry, say, 10 years or less? Quite a few. Okay, excellent. So what I did was I went back in and I added a slide as the first slide for this because I realized we really have to start, at ground zero. So for the newer folks in the room, I want to make sure that we get you off on a start. Now just flip side, how many of you have been doing this 20 years or longer? Yeah, there's a bunch of us. So if you see no hair, white hair, gray hair, that's the experience in the room. So yeah, I'm not going to, welcome. But just think of the money we save on shampoo. I mean, honest to goodness. Y'all younger folks have that to look forward to. So we're going to start off here, even though this is vertical bearing systems, what I want to do, and let me get this laser pointer working, that's the downside of the old folks is the whole technology thing. So let's see if I can get this laser pointer there. Well, it doesn't want to work. There we are. So we're going to start with just one slide on horizontal motors because most of us work on those, okay? So if we've got a horizontal motor, we know that the drive-in bearing is usually held captive or captured or located. Same thing, just different terminology we all use. And we know that the opposite drive end has to have room for thermal expansion of that shaft. So if we look at, say, a typical horizontal motor, if the drive end is held captive, if the outer race is clamped between the bearing housing and the bearing cap, then we have to have room for that opposite end for thermal expansion of the shaft to grow thermally and not preload the bearing. As a rule of thumb, 10 thousandths of compression, if you will, is about equivalent to 10,000 pounds of thrust load. So if we run a motor in the shop, no load, runs great, customer installs it, and 8 hours later, 12 hours later, 2 days later, the back end bearing fails, it's probably because it didn't have enough room for thermal expansion. So with a horizontal motor, what we're after here is to make sure that the bearing itself has room to move in the housing, so for that whole thermal expansion. Neat trick for the new folks in the industry. Easy thing to remember is how much coefficient of thermal expansion is for carbon steel, and it's 5 zeros, so 0.00000067. So if you just remember that mnemonic, 567. So it's 0.5 zeros and 67 per inch of shaft length per degree C of temperature rise. So the rule of thumb is 10 thousandths per foot of shaft length. So pretty easy thing to remember for how much room we need for thermal expansion. So now let's switch that forward to vertical motors. With a vertical motor, you can consider that top bearing assembly whether it's one thrust bearing, 2 or 3 thrust bearings, a spherical roller thrust bearing, a hydrodynamic, what many of us think of as a Kingsbury bearing. Regardless of that complex bearing arrangement in top, that's our locating end. So our room for thermal expansion has to be on the bottom. So the lower end, the bottom guide bearing, is where we need our room for thermal expansion. So if I look at one thrust bearing, 2 thrust bearings thrust down, two down, one up, or one up, one down. A lot of complex possibilities, but the consideration is that's my located end, that's what's clamped, and I just need room for the bottom guide bearing for the shaft to expand thermally. I think a lot of us have seen this. Somebody else has repaired a vertical motor and they didn't know what y'all know, and the bottom guide bearing wipes out and within just a couple of days of operation. So what you see here on the left, that's the result of somebody not setting that end thrust or that end play. Again, different terminologies that we all use for the same thing. So what we have to have is we have to have room under that bottom guide bearing in the housing for thermal expansion of the shaft. How many of you are mechanics or have mechanicked? Bunch of us? Okay. So we know we set the end bell up, put the bearings on the shaft, pick up the rotor, set it in the bottom end bell, and at that point, the bottom guide bearing supporting the weight of the rotor, right? Put the stator on, top end bell, our thrust bearing arrangement, and at that point, we have to adjust our thrust, and the way we're doing that, we're just picking up the bottom guide bearing as high as possible so that we know we've got that necessary room underneath the outer race of the bottom guide bearing for thermal expansion of the shaft. So that's our key right here. So if the last people to work on the motor, or if the customer changed a thrust bearing on site themselves because they were in a real critical short shutdown and they didn't do it right, then what you and I see with the motor incoming is a failure of that bottom guide bearing. And just almost guaranteed when we see something like this, it's because somebody didn't set it up right when they assembled it last. So it's a good clue for us. So now let's look at the different thrust bearing options. So most of what we see are just angular contact thrust bearings. So that 7300 series or 7200 series thrust bearing. And if we look at that, there are a lot of things that the last folks to work on it could do wrong as well. So if we look at this, we may have a different suffix, a different letter at the end of that bearing number. So for instance, if we have a 7320 bearing, if it's a 7320B as in Bravo, it means it's got a 40-degree contact angle. Same exact number, 7320, but with no suffix at all, then it's a 30-degree contact angle. And if it's a 7320C, then it may be a 15-degree contact angle. So if we look at that contact angle, that's just the angle off of vertical. So you can kind of see that if I've got maybe a 15-degree angle, then it's going to help stabilize from radial movement. Whereas if I've got a lot flatter contact angle, say a 40-degree contact angle, it makes sense, it'll carry more thrust load, but it doesn't stabilize it against that radial movement. So if we've got a two-pole motor with thrust bearings, it's more likely to have that 15-degree contact angle because it has to stabilize that so the top end of the rotor doesn't orbit and basically cause movement and vibration. And then we see what we here called a pump pack arrangement, where we might have 2 or 3 thrust bearings, but they're not all the same contact angle. And that's the place that the last people to work on the motor may have created a problem. So your customer, you know, Murphy's Law, you talk to the customer about why they're sending the motor in, and sometimes they don't really tell you until after you've repaired it and you've got it back to them, and you find out that the last people that worked on this worked on it 3 times. The bearings never lasted. They gave up. They sent it to you, but they didn't tell you all the rest of the story, right? So in those cases, someone else may have taken 2 thrust bearings out of the motor, recorded the number and the suffix letter off of 1 bearing, and ordered 2 of those. So what should have started life with perhaps a 7320C and a 7320B now just has 2 of one or the other, and the customer has either insufficient thrust capacity or it's unstable because they're running 3,000 RPM and, you know, in the rest of the world, or 3,600 RPM in North America. So matching up those numbers, if the manufacturer still exists, and if the manufacturer will share info, then by all means call the manufacturer, ask for a parts breakdown. You know, what's the parts breakdown, what are my bearing numbers on that parts breakdown? If they're not the same number, you know, that's your aha moment that someone else mismatched what was supposed to be in the motor. So those are important. Higher speed, lower contact angle, higher capacity but lower speed, say 4-pole, 6-pole, more likely to have the 30 or even 40-degree contact angle. So matching that up is really important. The other thing that a lot of us don't realize and realize very late in our careers is that if I have a machined bronze retainer bearing, which is what we prefer for oil lubricated for thrust bearings, we can have an inner race guided, an outer race guided, or a ball guided cage. And what we actually want is that ball guided cage because it has a bigger gap between the cage and the inner race and the cage and the outer race for oil to circulate through. So if I get a race guided or a ring guided bearing, then it's going to actually restrict how much oil can get in there and lubricate the bearing. So your bearing temperature is going to be higher. I'm not going to ask how many people already knew that. How many of you know someone else who didn't know that? So I find that works better. If I ask how many of you have made, you know, this mistake versus how many of you know someone else who has, all of us know someone else who has. So we're less likely to raise hands, you know, just human nature. So that ball guided and machined bronze retainer, really important for thrust bearings. And then a little bit better graphic, I really kind of feel like I need both graphics. So here we can see that here's the cage and it's almost in contact with the inner race on the shaft. So that's really constricting our airflow, our oil flow through. Whereas here on the ball guided, there's a pretty good gap between that and the inner race and between that and the outer race. So we're going to get a lot better oil flow through to lubricate the bearing and to cool it. And then when we start looking at multiple thrust bearings, I guess the first thing is that we don't get as much bang for our buck. So if we have a single thrust bearing and it's rated for 10,000 pounds of thrust, and we add a second thrust bearing, instead of getting 20,000, we're only getting 16 or 60% more, so we're at 60,000. So 3 bearings, we're spending 3 times the money and just barely getting more than twice the capacity of that single thrust bearing. So we tend to see manufacturers, when they can, rather than go to a stack of 3 or even 4 thrust bearings, we're liable to see a spherical roller thrust bearing, which has a much greater thrust carrying capacity, but the doggone things have quite a bit lower speed rating too. So there's always kind of a trade-off. So if we have a 3,600 RPM or a 3,000 RPM vertical motor, we're apt to see multiple thrust bearings, even though it's costing more money, because the speed rating of, say, a 6315 bearing might be 4,000 RPM, whereas a 63, or not a 63, a 29338, so the spherical roller thrust bearing, that RPM rating's about 1,000 RPM. So we're looking at differences in, you know, how fast a motor we can run as to how many thrust bearings we wind up having to use. And then, of course, the more thrust bearings they stack, the more complexity in getting oil flow through and cooling the oil, cooling the bearings. So our lubricant's there, of course, to lubricate the bearings and make them last. It's also there to dissipate heat, so we're wicking the heat out of the bearings. So if we have a stack of 3 or 4 thrust bearings, the oil coming into the first one is cooling that bearing pretty well, but by the time the oil gets 3 bearings up, we've got a much higher oil temperature, so a much smaller delta T between the oil temperature that's trying to cool that uppermost bearing and the temperature of the bearing itself. So we wind up with more difficulty in just controlling the temperature here. Just like ball bearings in a horizontal motor or sleeve bearings in a motor, that 80, 90, 100 rule. So 80 degrees C as an operating temperature, 90 C as an alarm temperature, 100 C is a shutdown temperature. So those are kind of a good rule of thumb to remember for temperature. How many of y'all are from the centigrade world? Okay, how many of you are Fahrenheit? Okay, Fahrenheit's a lot tougher. We should have converted back in the 80s when Congress said, no, we don't want to do that. But so anyway, so that 80, 90, 100 rule is pretty helpful. The other thing that, this is sort of a segue into the next slide. If we look at the 2 thrust bearings here mounted on a shaft, you can see we have a shoulder on the shaft, and that's resting on the inner race of this thrust bearing and this thrust bearing. And there's a couple things that I think you can see. One is both of these thrust bearings, they're angular contact, and they're both positioned thrust down. You can see the wider race on the bottom of the outer race and the wider race on the inner race at the top. So that's where that term angular contact comes in. We have a contact angle, kind of like what we're showing here. So because they're both thrust down, we don't have to have anything to retain the inner race on the shaft or on the bearing carrier. So all of our thrust load is transmitted through those 2 bearings, and the outer race here would be resting on a housing. And then if we look at this, same thing. We have 2 thrust bearings, and the contact angle is what we're trying to show here with that directional arrow. And when we look at how we set the thrust on that, and this is kind of a real common thing, but when we look at how we set that, again, our goal is we want that bottom guide bearing as high as possible in its housing so we have lots of room for thermal expansion of the shaft. So the way we set that is we're going to hopefully put a bottle jack under the shaft, or maybe we pick up the motor and rest the shaft on the floor. So we're pushing the rotor and shaft assembly up as high as possible. And now if we've done that, then the bottom guide bearing is up against the bearing cap on the bottom end. So now we've got it where we really want it to ride. And now we tighten this nut on top, and hopefully we're doing that with a spanner wrench, and just tighten that nut to snug it. And now we've picked up the shaft as high as possible, so the bottom guide bearing is where we want it. And now with that snugged, now we can set the motor on our blocks or on our table, and now we loosen that nut and we drop that somewhere in the ballpark of 8 to 15 thousandths, depending on really how you were trained and which manufacturer's motors you work on. And one manufacturer actually in their manual says to back it off a 1/6 of a turn. So it's not that 8 to 15 thousandths is a magic number. What we're after is we're just saying, hey, we want that bottom guide bearing as high as possible so that when we back off just a little bit, we're not preloading it, but we got lots of room under it for the thermal expansion of the shaft. So again, we want that 10 thousandths per foot of shaft length. So if you've got a pretty tall motor and you're working on it, then you know you've got maybe 5 or 6 feet, so you need 50 or 60 thousandths room for thermal expansion of that shaft. So that's really critical for us to make sure that it goes back into service. How many of you have a policy that you run an assembled motor for, say, 20 minutes or 30 minutes or even an hour? Okay, so you know long enough to take vibration readings and record amperage, gosh, that's really all we need, because we're not going to run that even for 8 hours and get the shaft up to its operating temperature. So, you know, run it long enough to record your vibration readings, record your currents, and anything after that, you're just wasting electricity and time. So, you know, just something to kind of keep in mind. Yes? So, yeah, if you don't mind, repeat it with the mic here. It just helps us with the recording. Yeah.
This statement you just made is specific to vertical motors, or is that any?
I would say for anything except a sleeve bearing motor. For a Babbitt bearing, white metal, plain metal bearing, I would run it until the bearing temperature stabilized. But yeah, absolutely, that's horizontal, vertical. If it's a ball bearing machine, then we really are just spinning our wheels running it because we don't get that thermal expansion. Yep.
So it's temperature stabilization, effectively.
Correct, temperature stabilization. And a few slides in, we're going to talk about the spherical roller thrust bearings that are spring-loaded, and they're kind of a real, not just an exception, but they're actually kind of a red flag that we absolutely don't want to run those too long. So I've got some pretty good pictures of what happens if we do. So, or maybe I should say some pretty bad pictures of what happens if we do. So yeah, good question, thank you. So when we look at this, whether you've got a US or a GE or Ideal or which manufacturer of vertical motors, the important thing really is that we want plenty of room for thermal expansion of that shaft. So there are cases where we have kind of unusual constructions, and at the very minimum, we could set up a dial indicator here and back off that nut to allow that shaft to drop and see how much room do we actually have for thermal expansion of the shaft. So especially, you know, vertical machines are pretty expensive, they're pretty unique, and it may have been repaired 5 or 10 or more times over, you know, over the life of that motor. So that just means there's a lot of potential for someone else to have made a mistake. So from that perspective, you know, setting up your dial indicator and making sure that we have plenty of room under that bottom guide bearing for thermal expansion of the shaft will hopefully keep us out of trouble here. So again, if you have the old mechanic who says set it at 8 to 12 thousandths, nothing wrong with that. If you have somebody that says 12 to 15, nothing wrong with that. It's just the number's not so critical as the fact that we want that bottom guide bearing as high as possible so there's plenty of room beneath it for thermal expansion of the shaft. Now here, and this is a place where the last people to work on the motor could have gotten your customer in trouble. Here we have thrust bearings where we have one thrust up and one thrust down. So it makes sense. I think it's almost intuitive if we just step and look at it. If we have a thrust bearing oriented thrust up, there's got to be something for it to thrust against. So if I look back here, we have 2 thrust bearings and they're both thrust down, and we don't have anything to clamp the outer races. So we know that motor left the factory intending for those 2 thrust bearings to be thrust down only. And here we have one where we have not only a clamping ring here on the outer race to capture the outer races, but we also have to have something to clamp the inner races on the bearing carrier. So the bearing carrier, the top hat, whatever y'all call it, this bearing carrier that the thrust bearings are mounted on, the inner races need to be secured on that. Sometimes we see a bearing lock nut like you see here. It's pretty common to see the little spiral lock snap ring because it doesn't give you as much disruption and churning of the oil. So if we have a bearing carrier and we look at it and one thrust bearing is oriented thrust up, then we have to have something capturing the inner races on the bearing carrier, and we have to have something clamping those outer races in the bearing housing. So if we don't have that, if we have one thrust bearing up and one down, but the housing looks like this, then that motor was not built for bidirectional thrust. It was not built to handle up thrust. And where we often see this is the customer has maybe changed the pump. Maybe they had a catastrophic failure, maybe they bought a better pump, and now they've put this motor on, and they said, well, we need thrust up capability, and if they had a shop flip one thrust bearing, then they have to have also made a provision to clamp the outer races here. If they don't do that, then they really don't have a thrust up arrangement. So what can happen is if they get a pretty horrendous up thrust, it may actually push the bearing carrier inside the inner races and displace it away from the shoulder. And now we're going to see some unstable, higher vibration, things of that nature. The other thing is, and I keep toggling back and forth, forgive me, but here when we're setting our in thrust the way most of us do most vertical motors, this is great for this. But when we're wanting that 8 to 12 thousandths or 8 to 15 thousandths of allowance for thermal growth of the shaft, we do that by loosening this nut, right? So we're dropping the shaft inside our bearing carrier. But if we have this arrangement, if we have at least one bearing that's thrust up, then that bearing carrier actually has to be clamped against the shoulder on the shaft. So we don't set thrust the way we do on a typical vertical if we have one thrust bearing thrust up. If we do that, we're actually allowing room so the bearing carrier is now loose on the shaft, and it's going to move up and down, and we dismantle the motor and we pull the bearing carrier, and you see a lot of fretting corrosion on the shaft and on the ID of the bearing carrier. That tells us that whoever worked on that last did not understand that if they've got a bearing thrust up, that bearing carrier has to be actually shouldered against the shaft shoulder, and it has to be clamped. So if that's not clamped, we're going to see that fretting movement on the bore of the bearing carrier, and that's really a good clue for us that someone else hasn't repaired it right. So thrust up bearing, the bearing carrier has to be shouldered against the shaft and held securely against it. So if a guy is setting, if one of your techs is setting in thrust using the method we do for, you know, the previous slide, then they're not doing it right. So again, if we have thrust up and thrust down, this bearing carrier needs to be shouldered on the shaft, needs to be clamped in position. And of course, and I know I'm repeating myself, but just really important that the outer races are clamped, so they're resting against the shoulder in the housing, and we have a clamp here. Some, well, notably US and GE may have a ratchet assembly, an anti-rotation device, and the shoulder on that may be what provides our clamping of the outer races. So we may have that design, we may have what we're showing here, but again, the outer races have to be clamped, and the inner races have to be secured on the bearing carrier, and the bearing carrier has got to be shouldered against the shoulder on the shaft. So those three things, and it's not surprising really, but we see that done incorrectly a lot. So once again, you take it apart, you see lots of fretting corrosion on the bore of that bearing carrier. It's a pretty good red flag for us that someone else didn't set it up right. So any salesmen in here? Okay, so this is really good talking point for the salesman when you go out and talk to the customer, you know. You don't want to be the donut delivery guy, you want to be the answer guy. So good information here. Yes?
During shop testing, do you have any thoughts on when you're testing a motor that has a ball bearing or a thrust bearing, testing it unloaded versus actually having some load to it?
Okay, so yeah, the question was about in-shop testing, testing it loaded versus unloaded. And it's a really good question. The first shop I worked at, we did a lot of petrochemical work and a lot of, pumping, vertical applications. And we spent a lot of time chasing our tail trying to trim balance verticals. And we finally kind of took a step back and said, okay, what are we doing wrong? And we were creating unnecessary work. What we found was the magnetic centering force on the rotor trying to center it in the stator. If we happened to have a motor where the rotor was setting a little bit low, the magnetic centering force was picking it up and the top end was orbiting, doing this number. So without a mechanical load holding down on it, we found out that we were not trying to fix a balance problem, but an actual, just a shaft orbiting problem. For us, the simple solution was when we ran a vertical motor in the shop, to take our vibration readings, we ran it at about half voltage. We knew we were running rated speed, or almost synchronous speed, but we knew that way the magnetic centering force was much lower, and we actually got consistently good vibration readings that were replicated when the customer installed it. Whereas before, when we were sitting here adding trim balance weights and trying to do the whole vector diagram thing, we were, yeah, I can tell by the way you're laughing, you've been through that too. It's no fun, right? So for us, that really made the difference. One retired engineer for a large vertical motor manufacturer told me that they had cases where a customer would insist on the hydrodynamic, the Kingsbury type bearing, which is much more expensive, even though their engineering department said we don't need that. We need a pair of 7320 thrust bearings. And in those cases, they actually assembled the motor or built it so the rotor was setting high, so the magnetic centering force provided the additional thrust load that bearing needed, which I thought was a pretty clever way for them to, two rules. Rule number one, the customer's always right. Rule number two, when the customer's wrong, see rule number one, right? So in their case, the customer said, no, this is what we need, and instead of saying, no, you don't, they said, okay, we can make the customer right. So, but yeah, for us at least, that half voltage for the vibration readings really was the easy solution. And our poor guys who were in charge of test running those, they really liked that better than trying to vector diagram and trim balance and all that rot. So we kind of have two options, and I'm not going to say right and wrong, but if we think about it, so if we look at the oil flow through, we have our stand, our sight glass here on the outside, and everybody knows we've got two marks on those, right? We have what's really a standstill level at the lower mark and a running level at the higher mark. And the reason that that's the case is, if you look here, the oil in this outer chamber is there airflow over the outside of it to cool the oil, and then the oil's kind of metered and regulated through a smaller hole, roughly 8 or 9 millimeters, 1/4 to 3/8 of an inch, kind of in that ballpark. And the oil comes in near the bottom and heat rises, so the oil comes in, hits the lower bearing, and then it's carried up, transmitted to the upper bearing and out, and recirculates with the oil in the outer chamber to cool the oil. So pretty simple setup. If we have this arrangement with the thrust up bearing in the bottom, it's not carrying any load, so there's not really much heat generated in that bearing. So our oil, when it hits the upper bearing, is a little bit cooler than if we had this set up here. So if we had the thrust bearing carrying the load on the bottom, as we do on the left, then what we wind up with is that oil's heated up a bit more before it hits the upper bearing. So both of those are okay, and you'll see different manufacturers use both setups. The engineer for vertical motors who I really kind of took to heart suggests this method simply because the oil temperature is going to be a little bit cooler when it hits the upper bearing than it is with this arrangement. So, you know, if you had a customer and their complaint was, you know, our thrust bearing temperatures are really marginal, if you look at it and let's say that they had the thrust carrying bearing on the bottom and the upthrust bearing on top, you could reverse those and you'd probably drop the oil temperature or the bearing temperature by maybe 5 or 10 degrees C. So it's not a huge number, but if your customer's complaint is issues with temperature, that's certainly something to look at. And for sure, I think the ball guided cage, the machine bronze retainer ball guided, is going to make a pretty significant reduction in temperature if they're using an inner race guided or an outer race guided. So those are just two little cheats that you can use to, you know, to try to reduce the bearing temperature a little bit. I'm not going to spend much time on this slide. This is the tilt pad or the, you know, the hydrodynamic. How many of you see these? Okay. So it's a dry start every time. It's an exceptional bearing if you've got, say, a big vertical hydro. So let's see, think about hydros. Starts once when in the spring, runs continuously, turns really low speed. You know, if you're a bearing, man, that's the application you want. That's a pretty good life for a bearing compared to 10 starts a day and, you know, that sort of thing. So low speed, clean environment, running indoors in a hydro plant, you know, down by the river. So pretty nice application for a bearing. It's a terrible bearing for an application where the customer might start it 2 or 3 times a day because it is a dry start. We do have some material on these tilt pad bearings in the paper, so I'd encourage you to download that. And if you have questions on them, by all means, email us, because I think they're pretty cool. You know, for the guy to have invented that back in the late 1800s, I mean, what a brilliant person to have come up with that. The older folks in here, which includes me, remember elementary school? And I know they don't have them anymore, but have you seen those sawhorses? Seesaws? So we had a balance and we had a big board and one person on each end, and so we didn't have internet, we didn't have computer games, so entertainment, the bar was very low, okay? So if you had that seesaw and you always knew not to get on that with the person who was kind of diabolical and who would jump off and then drop you at extreme speed. So that's really the principle behind this. It's really pretty simple. We have a steel precision machine piece with Babbitt bonded to the top. These are these thrust shoes that we see here on the top right. And if we look at those, they're transmitting the weight to this piece, which actually is sort of, it's a rocker. It's like that seesaw. So it's actually dividing the force between these two support pads and then this one supporting, transmitting to these two and so on. So it's a really clever way for, say, 5 or 7 of these pads to equally share the support, the weight of the thrust load on the thing. So really simple. Again, dry start. So great application for this kind of bearing would be that hydro. You know, 1 or 2 starts a year. It's a pretty good life for a bearing. So I won't really drill down into that too much other than to say that it's a low-speed bearing. It's a very expensive bearing. If you compare the cost of this bearing to a comparable thrust capacity spherical roller thrust bearing, this bearing costs about 30 times as much. So not something you want unless you really need it. So now I'm going to switch to what we see a lot for higher thrust capacity rather than stacking 4 or 5 thrust bearings up and significantly more expense and more cooling issues. What we have here is this spherical roller thrust bearing, and we see them with or without the springs here. And I'm going to toggle forward because I think an actual photo is still better for most of us than a graphic. So we have the bearing carrier here, and then this is the inner race with the tapered rollers, the spherical tapered rollers mounted on that. And this is the bottom guide bearing. So if we have the spring-loaded outer race supporting and pushing up, if we run this unloaded in the shop, that's where we really get into trouble, is those springs are pushing up with enough force that it preloads the bottom guide bearing, and you literally don't want to run that more than 4 or 5 minutes. If you run it for half an hour, you're going to wipe out that bottom guide bearing. So what we see here is you can see there's a very heavy thrust load all the way outside where the ball path should be. So all this damage on the bottom guide bearing is from the support springs under that spherical bearing pushing up on it. So this arrangement here, and I'm going to toggle back here because the graphic's a little better. So these springs are strong enough to support about 40% of the thrust load hanging on this. So if we had, say, 100,000 pounds of thrust load, the weight of the water column and so forth of what we're pumping, then those springs are sufficient to support maybe 40% of that. So they're really strong springs. So those keep that pushed up, and they're keeping the rollers in contact with the outer race so that when there is a momentary upthrust, it doesn't orbit and move out and cause the rotor to strike the stator bore or the shaft to strike the stand tube here and create an oil leak. So when we're setting the thrust on these, we have to set up and compress the springs, and usually we do that with a bottle jack, for example, pressing down on the bearing carrier to compress the springs, and then we set it like we do on the slide we looked at a few slides ago. So real important. Alternative to that I see some people do, and I don't think there's anything wrong with it, is they assemble it without the springs. They set the thrust for the maximum expansion of the shaft for thermal expansion, and they set the thrust, and then they use a depth micrometer and measure exactly where that bearing carrier is, and then they take the bearing carrier off, put the springs in, and reset that to that same distance. So now we still have that 10,000th per foot of shaft length. So here, what we're looking at, again, just the caution is anything more than 5 minutes, there's a risk of wrecking that bottom guide bearing. And then the thing that's come up fairly recently within the past couple of years is the height of the springs. If we don't have uniform spring height when they push up, if we had, worst case, let's say that we had a bunch of shorter springs on one side and longer springs here, then when we have that upthrust, it's going to cock everything, and when the thrust load comes back down, we get the impact damage on one side. So if you look at the outer race and there's some heavy chipping and damage to one side, it's a good possibility that we need to take a look at those springs. I've talked to 3 different manufacturers, engineers, and asked what the tolerance is for the spring length, and it's crickets. No answer. Nobody has, they don't, they actually didn't seem to have that information. I spoke with one shop recently. They ordered new springs because of the issues, and they got the brand new springs in, and there was a 20 or 30 thousandths difference in the length of brand new springs. So to me, that's kind of a potential problem. So helped one shop, and I know this is an enormous number of springs here, but this particular very large motor, they were seeing the chipping of one side of the outer race of the spherical roller thrust bearing. And when we started measuring springs, that's when this whole thing sort of came up as an issue. So we wound up, they set it up on a magnetic chuck with a surface grinder and took the springs all to the same length, and it solved the problem. So it seems like that was cause and effect. So kind of a unique one. So definitely something you want to do. And because the whole supply chain issue, sometimes you're going to find that maybe a customer, the last people to work on it, lost 2 or 3 springs, and maybe they just bought some springs online that seem to be about the same size, but they're not the same compressive strength. So lots of potential things that someone else may have done to create a problem that you guys are having to fix. So I think that's an important thing to look at for sure, is compare the spring lengths, especially if you see one come in with damage. And again, same setup, but here we've just got a few springs installed, and this one was kind of special. It had caps on the springs and Allen head bolts holding everything together, and once again, surface grinder and cleaning them up to the same height seemed to solve their problem. This one was really kind of an oddball. Major manufacturer of vertical motors, 1750 horsepower, 6 poles, so 1200 RPM in the 60 cycle world. And the way this motor was built, they had 6 holes underneath the area where the bearing retainer is, and they're a pretty heavy stamped steel retainer, okay? So they had 6 holes drilled underneath for oil to be injected up into the roller bearing area, and the motors were running fine for 10 or 12 years. Customer pulled it out, sent it in just for a basic recondition and cleanup. New spherical thrust bearing, ran fine in the shop, back out in the plant, and a couple of days later the bearings wiped out, over and over and over. And what we believe happened here was that this heavy steel cage that's guiding our rollers, you know, of course the outer race and the inner race, all of those dimensions are, you know, they're kind of set in stone. They're always identical, but they have a lot of latitude on how they build that stamped steel cage that's guiding the rollers. And what we decided must be happening was that they had a broader area here of this steel that was now blocking the airflow. And if you look at it, because it was running fine in the shop, those springs are lifting it up perhaps, you know, 1/8 of an inch or so. So, you know, enough distance, 3 millimeters, enough distance that they were getting oil lubrication of the bearing in the shop. And then when it was installed and the springs were compressed, now they were losing that gap. So that little bit of distance was enough to obstruct the oil flow. So kind of a real strange setup. Lots of heat discoloration, as you can see. The other thing is, I think you can see the number here. It's a 29338 spherical bearing, and that's something like 1,000 RPM limit for that size bearing in oil lubrication. So it probably needs to be a, you know, a quote-unquote high-speed bearing as well. So the manufacturer in this case agreed that, well, the solution is let's drill these holes out bigger. So they've been big enough for 10 or 12 years, but now they agreed that maybe drill these holes out bigger so we get more oil flow. So, you know, not a warm, fuzzy feeling when something's been working for a long time and suddenly they're saying change it and they're not sure why. So that seemed to be the difference here. So a couple things here, just mechanical issues. One is that if we've got the non-reverse ratchets, You know, GE likes the pin type, US likes that Ball-O-Matic with the balls, and in both cases, those have to be hardened. So if the last folks lost those pins and just made some out of cold rolled steel, you know, 1018 instead of hardened, then every time they hit the ramp, they're going to mushroom out a little bit bigger, and one day they go up and they don't come back down, and suddenly you don't have a anti-reverse ratchet. So, you know, those are things to watch out for. I almost shouldn't share this story. I was in a shop in Maine 30 years ago, and I happened to be up in the test area, and I looked, and on the wall there was a row of neat holes about like this diameter, and I thought, you know, what happened there? And the guy, he was pretty embarrassed, as well he should have been. A mechanic assembles the vertical. He drops the balls in that anti-rotation assembly, and then he thought, you know, I need to bump this for rotation. Should he have taken a magnet and taken the balls out? Yeah, I kind of think so. Or he could have put the collar on it that captures them, and if he had the wrong rotation, it wouldn't turn. Either of those would have been a good choice. Instead, he carried it over there, and Murphy's Law, he got the rotation right. So it was like a Gatling gun with steel balls that diameter, and punched a bunch of holes. You know, yeah, don't do that. He's really fortunate he didn't kill somebody, because it would have been closed casket. So that's an important thing. If you have an anti-rotation device, a ratchet assembly, you know, be cautious of that. There are designs where the top coupling on a hollow shaft simply rests on the pins on the bearing carrier, so you don't want to test run it with that because it's not bolted down. And I know common sense really isn't all that common these days. So, you know, it seems like nobody could be that stupid. Yeah, they could. So just something to be cautious of. The other thing that we run into is simply flange run out. A lot of our customers look at a vertical motor, and I can understand the logic. They say, well, I have a locating fit, a register on the bottom of the motor, and there's a corresponding register on the base, so they just assume they can set it down and it's lined up. But oftentimes bases settle, they rust, so they really do need to go through the alignment process. And then along that line are just the flange diameter, the recommended runouts for those, and then the rabbet diameter, and then the face runout. We do see, in some cases, we see people use shim stock on the bottom bracket to square that up to get the run out where it should be. That may be an option if the run out isn't severe, but we're really better off to remachine that bracket and true it up. Easier said than done would be to mark your high point and concentricity, mark the run out, set it up in the lathe or the mill, and duplicate that run out, and then true it up, put it back on, and see if you got it right. The other alternative is cumbersome on a large motor, and that's assemble it with a ball bearing in the top end instead of a thrust bearing, and set the whole motor up in a lathe and remachine it. But each of those are, you know, pretty cumbersome. So kind of reviewing here, but we want to just be sure that we have that room for thermal expansion of the shaft under the bottom guide bearing, so that when we put it in service, we know it's going to last. And again, if your customer says, gee, we put it in, it ran great, vibration was good, and 2 days later the bottom guide bearing failed, it's a pretty safe bet that somebody didn't set that thrust to allow for thermal expansion. And then again, just review, but if we have thrust bearings in opposite directions, we've got to have something for that to thrust against. So really critical that if we have a bearing set up, thrust up, the outer race has to be clamped, inner race has to be constrained on the bearing carrier, and really just as important, perhaps more so, is that bearing carrier has got to be shouldered against a shoulder on the shaft, a step on the shaft here. And I see an awful lot of cases where people will use the normal dial indicator, 8 to 15 thousandths, when they have this kind of bearing arrangement. So they're actually setting themselves up for, for failure. Okay, that's all I have. Questions?
In the past, I've used cage elongation to identify thermal expansion or axial side load. Is that a good indicator?
When you say elongation, what do you mean?
I'll take the bearing apart and check to make sure that the cage is tight around the balls, that it hasn't started to move that cage. If it's a steel cage, it's easy to see at the rivet point if it's starting to bow out. And that's always been my indicator of axial loading. But
Yeah,
I don't
that's-
know, I think I just came up with that through experiences, and I don't know that that's.
Yeah, I think that's legitimate, and especially if you're looking at a machined bronze cage where you can see there's eccentricity and heavy wear on one side, then that could be indicative of either excessive load or sometimes misalignment as well, if it doesn't seem to be concentric and, consistent. Anything else? War stories. Vertical motor you wish your competition had gotten. That's a whole nother session, isn't it? How to trick your competition into outbidding you on the motor you don't want. Okay. All right. Well, thanks, everybody.